Hello, everyone. So thank you for coming to another series of these alternative seminars. So today's speaker is Laura Rego. So Laura finished her PhD in 2021 at the University of Salamanca. And then she moved for her postdoc with Margarita Sala's contract to John Marango's group at Imperial College in London. And there she worked with David Ayuso on applying structured laser pulses for ultrafast molecular chirality. And in 2023, she moved to the group of Professor Fernando Martín at Autónoma University, where she continued her research on ultrafast science. And since January 2024, she's been a postdoctoral researcher at IMDEA Nanoscience, and recently she obtained La Caixa Junior Group Leader Fellowship, and she will be joining us at the ICMM in October, November. So, Laura, thank you very much for coming, and the floor is yours.
Hi, everyone. Good morning. Thank you so much, Alvaro, for the introduction and also for inviting me to come here to give this talk and present my work. I'm also very excited about joining the ICMM at the end of this year, so I'm very happy about that. So in this talk, I'm going to explain what I did during my PhD and my postdoc in London. The topic is using ultrashort structured laser pulses for ultrafast science. So this is the outline of the presentation. I'm going to start with a brief introduction about what is structured light and how we can generate these ultrashort laser pulses through the phenomenon of high-order harmonic generation. And then we will see some applications where we combine these two concepts. So we combine ultrafast attosecond pulses with structured light. And we can see what can we obtain from this combination. We will see some examples of how we can use this to control the properties of these ultrashort pulses, but also to obtain information about the target, which can be, for example, a chiral molecule. So let's start with the introduction. Let me explain what is structured light. So during this talk, what I mean when I say structured light, I'm referring to light beams that exhibit some spatial dependent properties. For example, these properties can be the phase, the intensity, or the polarization. So in these beams, in the spatial profile of these beams, we have some changes on the polarization, or the phase, or the intensity in space. We can also have structured lights in time, so we will be talking about temporarily structured light or spatially structured light. And structured light is very connected. What happened? Okay, it came back. So it's very connected to the angular momentum of light. So light can carry two different kinds of angular momentum. Can you hear me, or is it? Okay, thank you. So light can carry two different types of angular momentum. The spin angular momentum, which is the polarization of light. This is the direction of the oscillation of the electric field, and this is well known, and it has many applications in our day-to-day life. But also light can have another different kind of angular momentum, which is the orbital angular momentum. In these beams, this is a macroscopic property where the wavefront of the beam is twisted. It creates these helical wavefronts in space. And this kind of angular momentum, the orbital angular momentum, is connected to the vorticity of the beam. So let me explain this one a little bit more in detail. So these beams carrying orbital angular momentum are called vortex beams. And they have this structure. In the intensity, they look like a donut because we have this profile with a zero intensity in the center. And if we look at the phase, we see that the phase rotates in the azimuthal coordinate, which is in the transversal plane to the propagation direction. So this phase is rotating along this direction. It's changing. And in the center, we have a singularity of the phase where the phase is not defined. And that's why we call this light vortex beams, because we have this singularity of the phase in the center. And that's the reason why we don't have intensity there. So this phase rotation is characterized by the quantity that is called orbital angular momentum, which defines the number of 2 pi shifts that the phase does in this plane. So the higher the orbital angular momentum, the higher the change of the phase in this plane. And then if we look at the wavefront, we can see in a normal beam with no orbital angular momentum, we have more or less planar wavefronts, but then with orbital angular momentum, we see that the wavefront has this twisted shape, like an helical shape, and the higher the orbital angular momentum that we denote with this L here, the higher this rotation, this twist is. Okay, and these ones are very interesting because they can have very interesting potential applications. For example, they can imprint this rotation into particles, so they can be used to move particles. They can also carry more information than conventional beams because you can store each information in this orbital angular momentum number that can go up to infinite numbers. And also they are interested in fundamental physics or microscopy and other fields. Usually they are created with these optics elements like this wave plate that imprints this phase rotation. Okay, so now let's move to the other ingredient that we needed, which are the ultra-short laser pulses. And this is very connected to last year's Nobel Prize in Physics that was awarded to Professors Pierre Agustini, Ferenc Krauss, and Anne Luyer, for the generation of ultra-short laser pulses and the potential applications. So let me explain how these ultra-short attosecond laser pulses are generated. They come from a process that is called high-order harmonic generation, where basically what we do is that we use an intense infrared laser beam and we focus it into a target. This target can be a gas, a liquid, or a solid, but I'm going to use a gas along this presentation. So we focus it into the target, and this laser is very intense, so it's going to drive nonlinear interactions with the gas molecules or atoms. And from this highly nonlinear interaction, there's going to be an emission of high-frequency radiation. These frequencies can go up to the extreme-ultraviolet or even X-ray regimes. So this is a frequency conversion process that is highly nonlinear, so we can get very high frequencies with this. So if we look at the spectrum, a typical spectrum of the harmonic, high harmonic generation emission, it looks something like this, where I'm plotting the intensity of the different harmonic orders. We call them harmonics because these frequencies are emitted as multiples of the infrared frequency. So these harmonics can reach very high frequencies until we reach the cutoff with a high efficiency, with a losing efficiency. That this is what is happening here in what we call the plateau. So this is a quite more or less efficient way to obtain basically laser pulses in the extreme ultraviolet or X-ray regimes. Okay, so from the temporal point of view, this is also very interesting because these high frequencies are emitted in the form of very short laser pulses that are called attosecond pulses, so attosecond directions. This is a very, very short direction for these pulses. And in case you are not so familiar with this unity, we can remember that in 1 attosecond, we have a trillion of, sorry, in 1 second, we have a trillion of attoseconds. So 10 to the 18 attoseconds are found in 1 second. So it's a very, very, very short period of time, so short that in this time, light can only travel the distance of the size of a molecule. And these super short laser pulses are very interesting because they can be used as kind of flashes of a kind of camera to get information of ultrafast dynamics. For example, the movement of electrons that happens super fast, we can kind of get information from them using these attosecond laser pulses, and that's why they received the Nobel Prize and they were so important in this community. Okay, so now we have the two ingredients. Let's first explain how this process is happening from the microscopic point of view. So understanding what is happening exactly in the gas, so this emission of radiation is happening. And this can be explained following a very simple three-step model, where in the first step, here I'm plotting this atomic potential that is distorted by the linearly polarized laser field. That's why it's bended, tilted in this direction. And so the action of this linearly polarized laser field is creating a potential barrier here that an electron can go through by doing tunneling ionization. So the electron is first ionized, then the laser is going to accelerate this electron. First, it drives the electron very far from the atom, but then when the laser changes its sign, then it drives back the electron back to the same atom where it was before. And then when it comes back to the atom, this electron has acquired a lot of kinetic energy during all this excursion. So all of this kinetic energy is going to be released when the electron recombines. And it is released in the form of high-frequency photons. And this is the reason why we have these extreme-ultraviolet or X-ray attosecond pulses that are coming from this phenomena of high-order harmonic generation. Okay. So now we have seen what is structured light and how we can generate ultra-short laser pulses and how high harmonic generation takes place. So what happens if we combine these two things? And this is what we are going to be seeing in the rest of the talk. So first, let's start with a simple case. Remember these vortex beams where we have these twisted wavefronts. And let's see what happens if we drive high-order harmonic generation using this beam. So what happens is that the harmonics are also going to be vortex beams, because this is a very coherent process. And they are also going to have orbital angular momentum, which is going to follow a very simple conservation rule. So if one wants to understand how the orbital angular momentum of the harmonics behave, we can just first remember how the energy conservation is going to be happening. So, for example, for the 21st harmonic, what is happening in our system is that it is absorbing 21 photons of infrared frequency and then remitting all of this energy in the form of a single photon that has an energy that is 21 times the energy of its infrared photon, right? So just a simple conservation of energy. So what happens with the orbital angular momentum? So something similar. You have the 21 photons. Each one of these, for example, they have orbital angular momentum equal to 1. So this one here is the orbital angular momentum. And since this quantity has also to be conserved, then the ultraviolet photon is going to have an orbital angular momentum equal to 21. So this high orbital angular momentum means that the phase of this harmonic is rotating a lot in the transversal plane, exactly 21 times 2 pi radians in this plane. Okay, so let's make it a little bit more interesting. So now we are going to use two vortex beams. So one with L equal to 1, the same as before, and now another one with L equal to 2. A different orbital angular momentum. And we combine them and we generate the harmonics, and what we see is that the harmonics are also still vortex beams, but now each harmonic can have different values of orbital angular momentum. The reason why there is this distribution of orbital angular momentum values is because now we have different possibilities of absorbing photons from one or the other infrared vortex beam. So for example, for the 21st harmonic, we can either absorb all the photons with L equal to 1, or we can absorb some photons with L equal to 1 and others with L equal to 2, and then we will get a different orbital angular momentum value in the end. And we have all these different possibilities, so we get a spectrum of orbital angular momentum values for a single harmonic. But this spectrum has some values that are going to be in the center of the distribution and are going to be the main component of orbital angular momentum. And something interesting that we can do now is that we can control this main channel, this main orbital angular momentum, by changing the intensity of the relative intensity between the two vortex beams. So for example, if this one is more intense, then the main orbital angular momentum is going to be shifted towards lower values because we have more photons with L equal to 1 in our interaction. And then if the other one is the one that is more intense, then we will have more photons with L equal to 2. And then the main orbital angular momentum value is going to move towards higher values. right? So this characteristic is what motivated the work that I'm going to present now. This was done during my PhD at the University of Salamanca under the supervision of Luis Plaja and Carlos Hernández. Here we were the theoretical team, and we collaborated with the experimental team from GILA in USA, and also we had got some help from ICFO in the theoretical part. Yeah, sure. Mm-hmm.
One single electron takes all that angular momentum.
Yeah.
How can that be? What kind of state is the electron in with 21 h-bar angular momentum? Can that be explained in the three-step model, or?
Well, I've never thought about what is the state that the electron is during this interaction. I guess it has the same orbital angular momentum that is going to remit, but when it comes back, it has to come back to the same state that where it was before.
It has to come
So
with 21, right?
But it releases this 21 when it recombines.
Right.
So it only has higher OAM during the excursion where it is free.
Okay, so maybe another way to phrase the question, is the nonlinear process less probable if you have a finite angular momentum, finite vorticity, than with the kind of pulses that people use that have no vorticity?
It's equally efficient, yeah. Okay. There is no change because at each point in a space, each atom, for example, it only sees a field with a phase, but it doesn't see the orbital angular momentum. So, because if you think about the dipole approximation, then there is no spatial variation of the field. So at each single point is equally efficient, and then you just have the superposition of all these emissions. So, well, yeah, in thinking about that, maybe the electron doesn't also really see that the beam has OAM while it does this excursion, because it only is, for example, when we do the calculations, you just give the system an electric field with a phase, and then you get that the harmonic at each point has the different phase, and then the whole thing adds up to get the vortex beam. So, and I mean, there are other works where they consider that beyond the dipole approximation, how the atom sees the orbital angular momentum, and this changes the selection rules and stuff. But it's a different way. Here we don't need to go beyond the dipole approximation. Okay, so so now in this work we're going to take advantage of this superposition of vortex beams, where we have now we're going to generate light with a time-dependent orbital angular momentum. So to do so, what we do is that we go back to our combination of two vortex beams, and then now we're going to introduce a time delay between them. And then what we get is that this is going to be our driving beam, and we are going to use it to drive high-order harmonic generation. So if we now look at the 21st harmonic, for example, then at the beginning of the interaction, we only have photons with L equal to 1, and then the 21st harmonic is going to have L equal to 21. But as time gets passing by, then we start to get photons with L equal to 2. So that is going to increase the orbital angular momentum of this harmonic. So it's going to from 21 to 42 along time. So this is the way that we use to generate a time-dependent orbital angular momentum, which is done thanks to the process of high-order harmonic generation that combines the different number of photons that we have in the infrared field to generate this time-varying orbital angular momentum in the 21st harmonic. So Now here we have the setup of what was done in the experiment. So basically we have here the two infrared vortex beams. And then if we look at the orbital angular momentum as a function of time, then we see that for this, in this case, the 17th harmonic, this orbital angular momentum is evolving in time, is increasing almost linearly with time for this beam. And this slope of this tendency is what we call the self-torque, because it's the derivative of the orbital angular momentum along time. However, measuring this in an experiment is very difficult, because you will need to very precisely measure the phase of your harmonics and how this evolves in an ultrafast way. So in order to measure this in an experiment, we were very lucky to find out that this time-varying orbital angular momentum leaves a signature on the frequency of the beam. And in particular, what we see is that the frequency of the beam that we have, here we have the spatial profile of the beam, this frequency is going to be chirped, so it's going to change spatially as a function of this azimuthal angle. So for each harmonic, the frequency here in this case is going to be increasing along this direction. It's changing spatially. And the slope of this change is going to be the same value of the variation in time of the orbital angular momentum. And this is the way that it could be measured then experimentally. This is the theoretical simulations, where you see here, this is the azimuthal angle that we got here, sorry, in this picture, this angle here. Oops. So now we have it here, and we see that for each harmonic, there's a positive slope along this angle, this chirp, and the value of this slope is exactly the value of the temporal variation of the orbital angular momentum. And in the experiment, they measured the same. And we can also control this by changing the time delay between the two infrared pulses. Then we get a different value of this self-torque, of this slope of the time-varying orbital angular momentum. Now, let's see another example of how we can use structured light in high harmonic generation, but instead of just controlling the orbital angular momentum, we're going to use it to control other properties of the harmonics, in particular, the frequency. So this was also done from the theory side at the University of Salamanca, and then the experiment was also done at Gila. And in this case, what we are going to use is a driving beam that is a combination of two vortex beams, one of them with L equal to 2 and the other L equal to -3. So when we combine two vortex beams and one of them has negative orbital angular momentum, means that the phase rotates in the opposite direction. And this creates what is called a necklace beam, because the intensity has this pattern that looks like a necklace with these petals. And here we are also plotting the phase of each of these petals. That you can see more or less each petal has a different phase that changes constantly. Okay, so we use this beam to drive high harmonic generation again. And what we see now is that for certain harmonic orders, there is this strong emission on axis that looks like a needle. So it's very intense in this center of the detector. And what is interesting is that if we look at how this evolves in time, how is the temporal behavior of this emission, we can see the following. So since here we have different phases, this means that our harmonic emission is going to be time delayed at each point here at each petal. So it's more or less like having 5 sources of high harmonic generation that have a different time delay between them. So that means that when the harmonics travel to the detector, to this point in the center, they're going to arrive at different times. For example, we can see that this red one arrives first, then the yellow one arrives, the harmonic emission from that, then the green one, and so on. So they arrived, the harmonic emission arrived with a different time delay here at the detector. So this can be seen here, where we represent the temporal profile of this harmonic emission. in usual high harmonic generation, what we get is 2 harmonic emissions per cycle. So let's say that the periodicity of the emission is 2 per cycle. However, with this scheme, we get a much higher repetition. So because we have all these 5 sources, and then we get that the harmonic emission is 10 emissions per cycle. So we are increasing the periodicity, of this harmonic detection here. And since we increase the periodicity in time, this means that if we now look at the harmonic spectrum, we are going to have fewer harmonics in our harmonic spectrum. So in gray here, these are the normal typical harmonics, that we all have all the odd order harmonics. But however, since we have increased this periodicity, we now have less harmonic orders here in blue than the ones that we got before. So we can control the harmonic spacing. The frequency difference between adjacent harmonics is now higher because we increase the temporal periodicity using this necklace beam. And we can change the orbital angular momentum quantities in our necklace, and then we can change the line spacing between the harmonics from the spectral point of view. And they also see this in the experiment. So, for example, here in the theory, we only generate the 15 and the 21 harmonic orders, and in the experiment, they also see this. So basically, what we do is we are suppressing some of the harmonic orders. So in this way, the orbital angular momentum can also be useful to control the temporal and spectral properties of these harmonics. Now, let's see another way where orbital angular momentum can be useful, and in this case, it's going to be used to control the polarization of these harmonics and of these attosecond pulses. And this was also done in collaboration with Gila, where they did the experiment, and also with Antonio Pipcon from the UAM and ICFO. So, this work was motivated for the question, can we generate circularly polarized attosecond pulses? So these attosecond pulses that won the Nobel Prize were always linearly polarized. And after that, many people started to work in trying to get schemes where these attosecond pulses have different polarizations, for example, circular. And this is what motivated this work. So why is it not so easy to generate attosecond pulses with circular polarization? So generally, when we have this harmonic generation, we can see it in this simplified picture here, where we have linear polarization of the electric field, and then it interacts with our atom where the electron is ionized and then goes very far from the atom, and then it comes back. However, if we use a circularly polarized driving field, then the trajectory that the electron doesn't come back to the atom, or if it does a little bit, it's super, super inefficient. So we cannot just simply use a circularly polarized driving field to generate circularly polarized attosecond pulses. It's not as easy as what we did with the vortex beams, where vortex beams were converted into extreme ultraviolet vortex beams. So what can we do? One of the schemes that was developed for this was using what is called a bicircular field, where there is this combination of one beam with circular polarization and frequency omega, and another beam with the double frequency and circular polarization but counter-rotating. By combining these two beams, the resulting electric field has this trefoil shape, like this. And this is how it evolves in time, right? So if now we look at the dynamics of the electron doing high harmonic generation, it does actually kind of recombine because it follows this shape of the trefoil. So it is a way to still maintain the efficiency of the high harmonic generation. And if we look at the harmonics that are generated, they are circularly polarized. Right circularly polarized for the blue ones and left circularly polarized for the red ones. The problem is that if we look at the polarization of the attosecond pulses, they are still linearly polarized because they come from the combination of all these harmonics. So we are integrating all of them, and at the end, they are still linearly polarized. So how can we solve it? And the idea is that what we can do is that we can try to remove from the picture, let's say, the left circularly polarized, we get rid of them, and we maintain only the right circularly polarized harmonics, so then the attosecond pulses would be circularly polarized as well. But how can we remove them? Because it's not as easy as putting a polarizer, because this is in high frequencies, so they don't work in this regime. What we can do is to separate them spatially by using, again, vortex beams. So if we introduce the vortex beams into this bicircular scheme, what we do is that at the end, this right and left circularly polarized harmonics are going to be separated spatially. So basically, this is the harmonic spectrum and the divergence profile. And for the right circularly polarized harmonics in blue here, these ones, they have lower divergence, so they have a smaller ring, while the left circularly polarized ones have higher divergence. So the total harmonic beam is separated in two rings, and we can filter out one of them if we want, with an iris or something like that. And then the harmonics, since they are separated, result in attosecond pulses that are actually circularly polarized. And then another thing that we can do if we want is to, following the same ideas with the time-dependent orbital angular momentum, if we now use two of these beams and we introduce a time delay between them, then we can get attosecond pulses that have a polarization that changes in time, so it changes from pulse to pulse. And we can control this helicity. Okay, so far we have seen three ways in which the orbital angular momentum is allowing us to control different properties of the harmonics, like frequency, polarization, etc. So we can generate attosecond pulses with designed properties. But another thing that we can do is to use structured light to get information from the target, from the sample where high harmonic generation is happening. And in particular, we are going to use it to study chiral molecules. So this was a work that we did in Imperial College in London with Dr. David Ayuso, who is an expert on chirality, and also with the help of Olga Smirnova and Ms. Ivanov from MBI. Let me first introduce you the concept of chirality, in case it's not so well known. So basically, an object is chiral when it is not superimposable to its mirror image. And the typical example are our hands, because they are the mirror image of each other. And no matter how we rotate them, it's not possible to perfectly superimpose them, right? And these two versions of the chiral object are called enantiomers, especially when we are talking about molecules. So we will be talking about the right-handed enantiomer and the left-handed enantiomer of the chiral molecule. And chirality is a very important property because of many reasons. First, it's a universal property, so we can find chirality in particles, molecules, animals, and even galaxies. And in all these systems, having right or left enantiomers is going to have some effects on how they behave. So, for example, if one wants to create a medicine, one enantiomer can be good for the medicine, while the other enantiomer can be, for example, poisonous. Or in industry, one enantiomer is useful for some application, and the other enantiomer it isn't. And they can even have different smells. For example, the carbon molecule has different smells depending on if you smell the right or the left-handed enantiomer. It can be meat or cardaway. So it's very important to distinguish between the two. And however, this is not so easy. So usually to distinguish between the two enantiomers, what we need to do is to make them interact with another chiral object. And this object can be light. So the usual standard methods to investigate chirality use circularly polarized light, and what they do is that they just measure the difference in absorption. So one enantiomer is going to absorb more of this circularly polarized light if it is right-handed, for example, and the other is going to absorb less. And this difference is very small, but can be measured, and that's how you measure the enantiomer that you have. However, now these methods have some limitations. They are not so efficient, and we can look for new methods that improve the enantiosensitivity, and also that they can be used in an ultra-fast way. And there are different methods, so I'm not going to go into detail, but what is important for us now is that driving nonlinear interactions is useful in this scenario because chiral effects get stronger. So for that reason, we are going to look at the nonlinear response of the chiral molecules when we come just with a circularly polarized, well, elliptically polarized laser field in this case. So our polarization is here in this plane, and we are propagating in the horizontal direction. So now we are drawing here the induced polarization, and we can distinguish between the left-handed enantiomer and the right-handed enantiomer. In order to see this more clearly, we can just represent this induced polarization using these arrows here. What we can see already in this plot is that for one enantiomer and we compare it with the other, the difference is found in this horizontal direction, in the same direction of propagation, and the rest is more or less kind of the same. So if we draw this in this scheme, we can see that there are two components in the y and x directions parallel to the polarization that are achiral. That means that they are the same for the two enantiomers, while the difference is found in the components that are going in the zeta direction in the direction of propagation. So these two components in the induced polarization is where we find the difference for one enantiomer and the other. So for example, for the left-handed enantiomer in green, it goes forward, and then for the right, it goes backward. So basically, there is a difference in sign in this direction. And what we want to do is to measure these components, because then we would be able to distinguish between the two enantiomers. However, the problem is that since they are parallel to the propagation of the laser, they are not going to, the light that they emit is not going to survive phase matching, so it's not going to be possible to measure them because of the direction that they have parallel to the propagation. So these components are hidden for us. How can we observe them? What we can do is to try to rotate this scheme, so trying to be able to imprint this dipole moment in the zeta direction, trying to rotate it so it can be measured in the y direction. So we want to rotate all of this scheme. To do this rotation, what we need to do is to rotate, to tilt the polarization of the laser field. So how can we rotate the polarization of the laser while keeping the direction of propagation constant? Because usually we have direction of propagation, and then the polarization is in the transversal plane of this direction of propagation. But this is not always like this. We can also get components in the polarization that are parallel to the propagation direction. And a method to do this is by tightly focusing the laser beam. So if we create a laser beam that goes to a very small spot in space, this creates a longitudinal component in the polarization. This comes just from the Maxwell equations. So basically, at the beginning in our laser, we have normal elliptical polarization perpendicular to the propagation direction. But then, as we get close to the focus, this direction of the polarization is going to get tilted in these blue planes that we have here. So we are going to place our target here, where this polarization is tilted. This tilt angle is going to change spatially. So here you can see that it's negative, and here it is positive. So we can draw it here. This is the tilt angle, and it would be changing continuously. So this is not something that breaks in the middle, but it actually varies continuously in this green direction. And also, we're having a spatially varying ellipticity. So our beam is a structured light because we have a structured polarization. This is not a vortex beam anymore, but this is still a structured light because the polarization is changing spatially. Now, let's look at what happens now to the induced polarization. Now, the chiral components that are the pink and green one, the pink is for the right-handed enantiomer and the green for the left-handed enantiomer, they are not parallel to the propagation direction anymore. So now they can be projected into the y direction here, where we are going to have the interference between the chiral components and the non-chiral ones, that is in blue. So the non-chiral components are going to serve as a reference signal where we make this interference with the other two. So we're basically creating an interferometer here. And we also have the same thing in other points in space, because as we saw before, this tilt angle is changing spatially. So in other region here in the left side of the beam, it would have a negative sign, but we still have this projection and this interference happening in the y direction. Okay, so since this is changing in space, this angle, we not only have this interferometer, but it's also going to change spatially. So if we look at the harmonic, in this case, the slit harmonic order, we will see that it's asymmetric in space. This is the x direction, where we have our molecules and our spatially varying field. And as you can see, for the right-handed enantiomer, we have a different intensity and phase. Phase is the dotted line. Than from the left-handed enantiomer, where we have this other intensity and phase. And this difference comes from here, this interference that is different from one enantiomer and the other, because you have opposite sign in these two components. Okay, so this is what happens in the near field, so in the plane or the target. And now what is interesting here is that since we have this bended phase, that is bended to one direction for the right-handed enantiomer and to a different direction for the left-handed enantiomer, this means that when light propagates, it's going to be separated in space because of this phase bending. And what we will see at the detection is that the emission from the one enantiomer is found at this spot, and for the right-hand enantiomer is found at the right spot. So they are spatially separated. And we can see this in these two peaks. So basically, if we have a sample and we don't know which enantiomer we have, by measuring the position of this peak, we will be able to distinguish between one enantiomer or the other. And if we have a mixture of both enantiomers and we want to know the enantiomer excess, which is the difference in concentration of one or the other, we can extract the enantiomer excess just by measuring the position of this peak. So this peak is going to move to right or left depending on the enantiomer excess of our sample. So this was also another example of how this structured light, where we can control the interference between different nonlinear interactions, allows us to separate light and space, and in this case to do it in order to obtain information from the target. So with this, we arrived at the conclusions. So what we first saw is that we can use a structured light with high harmonic generation to control the properties of the harmonics and the attosecond pulses, either by spatially structuring the beam, which allowed us to separate different light emissions to control the frequency, the temporal profile, or the polarization of these attosecond pulses. And also, we could structure these laser beams in the temporal domain to get time-dependent orbital angular momentum or time-dependent polarization in the attosecond pulses. Then we finally saw that we can also use this combination of structured light and high harmonic generation to get information from the target, and in this case to get information from the chiral molecules, where the light emission is going to propagate to one direction or the other depending on the enantiomer that we have. So with that, I would like to thank you very much for your attention, and if you have any questions, they are very welcome.
So great talk, thanks. So I I'm wondering about the way you create these beams, the finite L beam in the first part.
Mm-hmm.
You say you just put an optical element that is kind of chiral in a way, and that filters out all angular momenta except L equal 1, or creates L equal 1.
Mm-hmm.
Do you get like pollution of L equals 0 still? And if you do, can you actually filter out different L's optically, like you do with a polarizer?
Mm-hmm. That's a very good question, thanks. So, yeah, this is the typical optic element that is used to generate these beams. So it's just plate where there is a the thickness of the plate is changing in the azimuthal angle. So it is thicker here, for example, so it delays the beam there, and this is what creates this helical form. So in experiments, yes, it's very difficult to get super pure orbital vortex beams. They are able to get quite good modes with very little pollution if the orbital angular momentum is low. So for L equal to 1 is it's kind of easy. Well, I don't know because I'm not an experimentalist, but it gets more complicated when you want to generate higher orbital angular momentum. Then filtering out like afterwards is not very easy as far as I know. Maybe there are some experimental techniques that I don't know, but usually it's a bit complicated to kind of filter out modes aside from the way that they are generated. There are other methods to generate them using diffraction, for example, kind of fringes that from diffraction they also generate OAM beams and other kinds of setups. But yeah, I mean, it's not so easy as for example, the polarization, but I guess it's still in polarization. When you use a polarizer, there's still probably a very, very small percentage of not pureness. And these methods only work when you want to do vortex beams in the infrared or visible regimes. If you want to do them in X-ray and extreme ultraviolet, then it becomes more complicated because these optical elements are transparent and then they don't really imprint anything. So then, yeah, you have a lot of contamination, let's so to speak. But that's one of the reasons why it's so interesting to do this with high harmonic generation, because then you can transform an infrared vortex beam into extreme ultraviolet or X-ray vortex beams, which is much more efficient and pure than trying to do it with optics elements directly in this part. But yeah, of course, I don't think I don't have any picture of a experimental vortex beam, but when they are in the infrared with L equal to 1, they look quite pure. But then in the harmonics, then you start to have more impurities.
Hello? Okay. So I have a question on the self-torque because so this time-dependent orbital angular momentum depends on the trajectory of the electron, I guess. And so different trajectories of the electron, different subcycle dynamics will give different, let's say, frequency chirps to the azimuthal angle. So I guess for an atom could be kind of boring because
Mm-hmm.
It's kind of boring because you have this phase that I guess, I don't know if you consider short trajectories.
We have both trajectories, and well,
So
yeah.
my question is like this could be interesting maybe in solids or so to see different phase jumps between bands or whatever that the electron trajectory does to measure just the chirp of the azimuthal angle, which I guess is easier than just the phase of the harmonics.
Yeah, that's a very good point. So regarding the trajectories, if you wonder how is the orbital angular momentum for the different trajectories, I don't have exactly the plot here, but here in this distribution, the ones that are in the middle come from the short trajectories, and these ones come from the long trajectories. So if you only look at the long trajectories, for example, you don't have this, and this is more or less constant like this. So the long trajectories have very, very broad distribution of orbital angular momentum. It's not like the center is shifted, it's the same, the center, but for the short ones, you get all these main components and with less distribution, while for the long ones, you have much more distribution of orbital angular momentum. So yeah, by looking at the orbital angular momentum, you get some information from the trajectories. But in the self-talk at the end, we basically only see this main 2 or 3 channels, so which basically come only from, a little bit from the short, long, but basically mostly from the short trajectories at the end.
Yeah, so this is the question, right? Because in solids, you don't know if you have a short trajectory or you have different types of mechanisms
Okay.
to create a harmonic generation.
Yeah.
For lower than harmonics, right? It doesn't need to be the plateau. It can be also for lower than harmonics.
Yeah, well, for the lower than harmonics, we don't see this so broad distribution because we also checked and it was more like this. But yeah, what you said is right. I mean, you can, by looking at this orbital angular momentum spectrum, you can have distinguish if the electron came from a short or a long trajectory. Maybe you would need to know a little bit beforehand how it should look, I guess. But yeah, I think, yeah, that's a good point. Thank you. Good luck.